Hello students, in this video we will see about discriminative and generative models. So the discriminative model objective is to determine the decision boundary. So one side of the decision boundary belongs to class 0, other side belongs to class 1. It is applicable for two class classification problem. In case of generative model, the model will try to learn about the distribution of data instead of directly relying on decision boundary. These are the two major differences of discriminative and generative approach. Let us consider a data set with n features x1, x2, etc. up to xn, and the output can be either 1 or 0, which is nothing but a binary classification problem. So we need to determine the probability of y equal to 1 given x, or we need to determine the probability of y equal to 0 given the data set x. So in case of discriminative approach, the main objective is to determine the decision boundary which minimizing the error. So the decision boundary could be any line with separating the data sets. It could be like this or like this or like this, but the objective is to minimize the error. Error is nothing but the difference between actual as well as the predicted outcome. So in this case of generative approach, we will focus on the Bayes theorem. So the Bayes theorem, we already know the posterior equal to likelihood into prior by normalization, which doesn't rely on the decision boundary. It will rely on understanding the data distribution. So let us consider a simple problem, binary classification problem with only one features, which means only one data set is only one feature is available, and the output could be either 0 or 1. In this case, we have determined the output as blue or red. As it is only one-dimensional input feature, we have represented in a single line. If the data set consists of two features, then it will be represented like this. So here we are going to consider the data set with only one feature. The feature is represented in a straight line, and the outputs are either blue or red. In case of discriminative model, we will determine the decision boundary. In case of generative approach, we will determine the data distribution. There is nothing but a Gaussian distribution or normal distribution curve. So see, there are multiple decision boundaries are possible, out of which we need to determine the best or optimal decision boundary. In this case, this is the optimal decision boundary, because we can see the left side of the line is blue and right side of the line is red color with only one error. Consider this boundary, we could see both red as well as blue in both the cases. In this case also we could see some two red colors. Comparatively, the line, this is the best optimal line. So here a new data point or a new observation is given. So if we determine the decision boundary which is optimal is this, then we could see the data point new observation belongs to the red class. If this is the decision boundary, we could see this yellow belongs to the blue, but that is not right. In this case also we will determine the new prediction point as a yellow, which is also not right. So the optimal decision boundary is this line, and based on this optimal decision boundary, the new observation is categorized into either red class or blue class. In case of generative approach, let us assume a new data point that is yellow. We need to determine either it belongs to a red class or blue class. As I said already, the generative approach doesn't rely on determining the decision boundary, rather than it try to determine the data distribution. So as the data are normally distributed, we can draw a normal distribution curve, also known as a Gaussian distribution curve. We are just making an assumption that if we draw a curve like this, all the data points will come under this category. So this case will determine the mu as well as the sigma, that is the mean and the standard deviation. It will learn entire data distribution. Okay, so it will average the data, it will determine the standard deviation between both the previous values as well as the next values. So by this case, it will understand how the data are spread over the entire input space. So when a new point is come, it will determine the probability of both the classes, the probability of red as well as the probability of blue. You can see the blue line touch here as well as the red line touches here. So the probability of red is greater than the probability of blue. So we can conclude that the new data points belong to a red category. Similarly, if the new observation comes here, we could try a new line. So here we could say only blue class is available, so we can conclude it is a blue category. So if the data point comes here, we'll draw a straight line, which is nothing but determining the probability of both the classes. The probability of blue is higher than the probability of red, so we can conclude the new observation belongs to the blue category. The problem here is if the data is not normally distributed, or if the data distribution is not Gaussian, then there will be misclassification. So in the previous case, you could see all the data points are distributed in a Gaussian manner. So in this case, see here there are some outliers. These are some of the outliers. So I am drawing a normal distribution curve like this, and I am trying to, as usual, I am trying to determine the mean, standard deviation, and trying to learn the spread of the data. And a new data point comes here, and I am determining the probability of both red as well as blue. Here you can see the probability of blue is higher than the probability of red, so I can conclude it belongs to the blue class, but actually it comes under the red class. So it is the major problem. The generative model doesn't work well with outliers. So in this case, if the data is not normally distributed, we can go for some other distribution like chi-square, right? So in this case, the data point will be spread like this, and in this case it will spread like this. Okay, so this is not a normal distribution curve. It belongs to some other distribution, and we have to follow that. If it is Gaussian distribution, then the data has to be distributed in a Gaussian manner. That is nothing but if we draw a normal distribution curve, all the data points should be fit into this, similar to this category. There should not be some outlier. So the drawback of generative model is that, so the generative model have more impact on outliers. It doesn't work well with the outliers, as well as the cost of the generative model is high. So the discriminative models are computationally cheap when compared with the generative model. So let's look into some mathematical concept of probability discriminative model as well as the probabilistic generative model. So here we'll see how the mathematical concepts influence the choosing of optimal decision boundary as well as the determination of the Gaussian curve. So we could see two problems. One is two-class classification problem, another one is multi-class classification problem. So two-class classification problem is nothing but we can have either this or that output. But in case of multi-class classification, we can have more than one or more than two categories of output. So in this case, we will go for logistic sigmoid function, and in case of multi-class classification, we will go for softmax transformation. This logistic sigmoid function we already know, we have studied in logistic regression itself. So the output is either 1 or 2. So either class 1 or class 2. So I am going to write a formula for probability of class 1 on given x, which is nothing but the probability of output is 1 on given x, which is a logistic sigmoid function. So sigma of ln of p into x given c1 into p of c1. So this is derived using the Bayesian formula. So the probability of c1 given x equal to probability of x given c1 into p. Similarly, divided with probability of x given c2 into probability of c2, which is nothing but log odds ratio. This we have already studied. The logistic function is nothing but the log of odds ratio, and we are going to take a sigma of it. So we know the decision boundary straight line is w transpose x plus b, or we can write it as w transpose x plus w naught. So this is the two-class classification problem sigmoid function formula. And for multi-class classification, we can conclude it with general term. We don't know how many classes are there. It is a multi-class. So instead of writing 1 or 2, I am going to write in general. So probability of x divided by ck into pk. So you can see that probability of c1 means in the numerator we have c1. The denominator could be something else. So in general manner, we can write for multi-class probability of ck given x, again ck, and here denominator we are representing some other symbol. This exponentiation represent it as a softmax function. As it is logistic sigmoid, we can represent notation sigma, and if it is a softmax function, we can represent it as a exponentiation. So 4 things we need to know about the probability discriminative model. One is fixed bias, logistic regression, iterative reweighted least square, multi-class logistic regression. So the fixed bias is nothing but it is represented with the notation psi of x. One thing we need to remember is we need to map the original input features into the new dimensional space. If the input is represented in 2D, we can convert it into 3D, similar to the kernel we have studied in support vector machine, right? So consider the data point here. So here I have two classes. The output belongs to class 1 belongs to red and class 2 is blue, anything. Red or blue is my output, but I couldn't draw any line here which separates both the classes. So it is a problem. So how can we rectify it? How can we rectify it? So I am going to consider a fixed bias function phi of x. So this phi of x will convert the given data into a newer dimensional input space. So we can draw a decision boundary here. So see here, I can't decide a decision boundary. So what I am going to do is I am going to apply two fixed bias function. So the two fixed bias function are, one is the curve and another one is the circle. On applying this function, we could convert this distribution of data into this distribution so that we can draw a decision boundary which separate the class 1 on another side, class 2 on another. That is the purpose of applying the fixed basis functions. So the logistic regression we already know, the probability of C1 given x is determined by sigma of y of x, and the formula is 1 divided by 1 plus e power minus a, and a is nothing but ln of the same formula which we have seen in previous case. So logistic regression we know, so I'm not focusing much here. Then iterative reweighted least square. So it is nothing but an optimization technique. So drawing a decision boundary is not an objective. Drawing the best decision boundary, that is the optimal decision boundary, is my objective. So optimization is nothing but improvisation of the performance. So this iterative reweighted least square will adjust the parameters iteratively to minimize the error between predicted as well as the actual outcome. So it is similar to the gradient descent. We will start with the initial guess and we will update the parameters iteratively using some formulas of gradients and Hessian. It will take some more mathematical concepts, so let us not deep dive into it. So we'll update the parameter iteratively using these formulas and we'll repeat the process until we get a appropriate results. So it is similar to the gradient descent used for optimization. So these are some of the formulas that is used to get an optimal decision boundary. Next we will see the probabilistic generative model. The same definition for two-class problem will use logistic sigmoid function, and for multi-class problem will use softmax transformation. The same formula which we have seen in previous slides is applicable. So the same logistic sigmoid function as well as softmax function can be used here. And two things we need to focus on the probabilistic generative model is the continuous input and maximum log likelihood. So in continuous input, if the data are not discrete, if it is continuous, we need to make some assumption of the same covariance matrix. So the same covariance matrix. So if all the classes share the same covariance matrix, then the output is linear. So our objective is to determine a linear input space. So if every class contains its own covariance matrix, then it is quadratic. So it will result in more complex space. So we need to maintain the same covariance matrix. So for that, we'll determine three things. So for given data set, so if there is n data and the output belongs to C1 or C2, we need to determine the prior probability pi as well as the mean mu1 and mu2 as it belongs to two class. So we need to determine two mu's and we need to determine the shared covariance matrix. This is very important. The shared covariance matrix mu1, mu2 as well as the probability, everything can maximize the log likelihood. So on determining this, we'll get a best Gaussian model. So let us not worry about much mathematical concept behind it. Two things we need to remember. One, if it is a discriminative problem, we need to determine the decision boundary. If it is a generative model, we need to determine the Gaussian model. So for the Gaussian model, we need to determine all these parameters: prior, mu1, mu2 as well as the shared covariance. For a decision boundary, we can focus only on the sigmoid function. Okay, that's it. Thank you.